Welcome! Today, we'll explore LeetCode problem number 1679, max number of k-sum pairs. This is an exciting problem that challenges us to maximize the number of valid operations where pairs of elements sum to a given target. Let's dive in and uncover efficient ways to solve it. In this problem, you're given an integer array called nums and another integer k. The goal is to perform a series of operations where, in each operation, you select two numbers from the array that add up to k and remove them from the array. The task is to determine the maximum number of such operations you can perform. For the input format, nums is the list of integers provided, and k is the target sum that pairs must achieve. The output will be a single integer indicating the maximum number of operations where the sum of two chosen elements equals k. To better understand this, let's look at an example. Consider the input nums equals 1, 2, 3, 4, and k equals 5. The output in this case is 2. This is because we can form two pairs from the array that sum to k. Specifically, the pairs are 1, 4, and 2, 3. After removing these pairs, the array becomes empty, and we can't perform any further operations. Therefore, the maximum number of operations in this case is 2. Another example is when nums equals 3, 1, 3, 4, 3, and k equals 6. Here, the output is 1. In this second example, the only pair that sums to k equals 6 is 3, 3. After removing this pair, the remaining array is 1, 4, 3. In this updated array, there are no other pairs of numbers that sum to 6. As a result, we can only perform one operation, so the maximum number of operations is 1. Let's look at a third example for further clarity. Suppose nums equals 1, 1, 1, 1, and k equals 2. The output here is 2. In this third example, the pairs that sum to k equals 2 are 1, 1, and another 1, 1. After removing these pairs, the array becomes empty, meaning no further operations can be performed. Therefore, the maximum number of operations is 2. Now, there are a few constraints and edge cases to consider. The array length can be as large as 10 to the power of 5, so the solution must be efficient. Numbers in nums and the value of k can be very large, up to 10 to the power of 9. Edge cases include small arrays where no pairs can form, arrays with no valid pairs, and scenarios with duplicate elements or very high values of k. Addressing these cases ensures the solution is robust and handles all input scenarios effectively. To solve the problem of finding the maximum number of operations where the sum of two removed elements equals k, we can start by considering a brute force approach. The intuition here is straightforward. We systematically check all possible pairs of elements in the array to see if their sum equals k. If a valid pair is found, those elements are removed, and the operation count is increment. This can be implemented using nested loops that iterate through every combination of numbers in the array. While simple to understand, this approach has significant drawbacks. The time complexity is n squared due to the nested loops, which makes it impractical for large inputs. Additionally, removing elements from the array adds extra overhead, further reducing its efficiency. For these reasons, while it's a good starting point to understand the problem, this method isn't viable for optimal performance. A more efficient solution involves using a hash map, which allows us to avoid checking all pairs explicitly. The key insight here is to track the frequency of each number as we iterate through the array. For any number x, we check if its complement, kx, exists in the hash map with a count greater than 0. If it does, it means we've found a valid pair. We then increment our operation count and decrease the frequency of both x and kx in the map. If the complement doesn't exist, we simply update the frequency of x in the hash map. This approach processes each element in the array only once, resulting in a time complexity of n. The space complexity is also n, due to the hash map. This method is significantly faster than the brute force approach because it avoids redundant calculations and directly targets pairs that can form the sum k. Another efficient strategy is the two-pointer approach, which works particularly well when the array is sorted. The intuition here is to use two pointers, one starting at the beginning of the array and the other at the end. By comparing the sum of the numbers at these two pointers to k, we can decide how to move the pointers. If the sum equals k, we've found a valid pair, and both pointers are moved inward. If the sum is less than k, we move the left pointer to increase the sum. If the sum is greater than k, we move the right pointer to decrease the sum. To implement this, we first sort the array if it isn't already sorted, and then use a single traversal with the two pointers to count valid pairs. The time complexity is O, n log n, due to the sorting step, and an additional O, n, for the two-pointer traversal. The space complexity is O, 1, since no extra data structures are used. However, sorting the array adds overhead, especially for unsorted inputs, making this approach less efficient in such cases. Among the approaches discussed, the optimized hash map solution stands out as the most practical and efficient. The hash map allows us to directly track the frequencies of numbers and check for complements in a single pass, eliminating the need for nested loops or sorting. This efficiency makes it especially suitable for unsorted arrays. The key observation here is that we can count valid pairs without modifying the original array, which simplifies the implementation and improves runtime. The aha moment comes from realizing that we don't need to iterate over all combinations or sort the array. Instead, we leverage the hash map to solve the problem in linear time. While the two-pointer approach uses less space, the hash map method avoids the sorting step, making it more versatile. Overall, the hash map approach strikes the right balance between speed, simplicity, and practicality, making it the best choice for this problem. In this problem, we are tasked with finding the maximum number of operations we can perform on an array where each operation involves removing two distinct elements whose sum equals a given value, k. The challenge is to maximize the number of such pairs we can find and remove. To solve this efficiently, we will explore two approaches, the two-pointer method and the hash map approach. Our focus will be on the hash map approach since it provides better performance. To begin, we initialize a hash map to store the frequencies of elements in the array. This data structure helps us quickly check the availability of complements for any given number. Additionally, we set up a counter to track the number of valid operations performed as we process the array. Now, we proceed to iterate through the array. For each number, we calculate its complement by subtracting the number from k. Using the hash map, we check if this complement exists and if its frequency is greater than 0. If so, we have identified a valid pair. We then decrement the frequencies of both the current number and its complement in the hash map to ensure they are not reused. At the same time, we increment our operation counter by 1. If the complement is not available or its frequency is 0, we simply update the hash map to increase the frequency of the current number. By the end of this process, the counter will hold the total number of valid operations performed, which we return as the result. The hash map is a crucial component of this solution because it allows us to check for complements in constant time. This is a significant improvement over a brute force approach, which would require checking all possible pairs, resulting in a time complexity of O, n squared. By decrementing the frequencies of both the current number and its complement immediately after forming a pair, we also avoid double counting, ensuring the correctness of our solution. These efficiency gains come from processing each element only once, giving our algorithm an overall time complexity of O, n. This makes the hash map approach not only faster but also more scalable for larger input sizes. The hash map serves as our primary data structure, storing the frequency of each element as we traverse the array. For instance, if we have nums equal to 1, 2, 3, 4, and k equal to 5, the hash map evolves dynamically with each step. After processing 1, it contains 1, 1. Once we process 2, it becomes 1, 1, 2, 1. When we reach 3, we find a valid pair with 2, and the hash map adjusts to 1, 1, 2 o'clock, 3 o'clock. This demonstrates how the hash map tracks and updates frequencies in real time. In terms of complexity, the algorithm runs in O, n, time for processing the array and uses O, n, space for the hash map. It also handles edge cases effectively, such as arrays with no valid pairs, duplicate numbers, large values of k, or negative elements. Let's walk through a specific example to see the algorithm in action. Given nums equal to 3, 1, 3, 4, 3, and k equal to 6, we start with an empty hash map. First, we process 3, whose complement is also 3. Since the complement is not yet in the hash map, we add 3 with a frequency of 1. Next, we process 1, whose complement is 5. Again, the complement is not found, so we update the hash map to include 1. When we process the second 3, we find its complement in the hash map with a non-zero frequency. This forms a valid pair, so we decrement their frequencies and increase our operation count to 1. Continuing, we process 4 and then the final 3, updating the hash map as needed. By the end, the hash map reflects all processed elements, and the total count of valid operations is 1. This example highlights the algorithm's efficiency and its ability to handle duplicates and complements dynamically. This Python code solves the LeetCode problem number 1679 max number of k-sum pairs using a hash map approach. The goal is to find the maximum number of operations where two distinct elements in the array add up to a given value k. We start by initializing a counter count to track the number of valid operations and a dictionary frequency to store the frequency of numbers in the array. As we iterate through the array, for each number, we calculate its complement, the value needed to reach k, and check if the complement exists in the frequency dictionary with a frequency greater than 0. If it does, we perform an operation by incrementing the count and decrementing the complement's frequency in the dictionary. Otherwise, we increment the frequency of the current number in the dictionary. This ensures we efficiently track the pairs without needing nested loops. The algorithm runs in O(n) time, making it optimal for large inputs. This is the Java implementation of the LeetCode problem max number of k-sum pairs, number 1679. The logic mirrors the Python implementation, using Java's hashmap to track the frequencies of numbers. The main differences include explicit type declarations and the use of Java-specific methods such as getOrDefault for handling default values in the hashmap. The solution iterates through the array, checking for complements and updating the frequency map as needed. This approach ensures the solution is efficient while maintaining readability. Let's start with the first example, where nums is 1, 2, 3, 4, and k is 5. We initialize a count variable to 0, which will track the number of valid pairs, and an empty frequency map to store the occurrences of numbers. In the first iteration, we process the number 1. The complement needed to sum up to k is 4. Since 4 is not in the frequency map, we add 1 to the map, making frequency equals 1, 1, and the count remains unchanged at 0. Next, we examine the number 2. The complement is 3, which is also not in the frequency map, so we add 2 to the map, resulting in frequency equals 1, 1, 2, 1. Again, the count stays at 0. Now, for the third number, 3, the complement is 2. This time, 2 is present in the frequency map with a value greater than 0. This means we can form a valid pair, 3, 2, we decrement the frequency of 2 by 1, updating the map to frequency equals 1, 1, 2 o'clock, and increment the count to 1. In the fourth and final iteration for this example, we process the number 4. The complement required to reach k is 1, which is present in the frequency map with a frequency greater than 0. This means we can form another valid pair, 4, 1, we decrement the frequency of 1 by 1, updating the map to frequency equals 1 o'clock, 2 o'clock, and increase the count to 2. At this point, we have processed all numbers, and the final count is 2, representing two valid pairs, 1, 4, and 2, 3. The output for this example is 2. Now consider the second example, where nums is 3, 1, 3, 4, 3, and k is 6. Again, we initialize count to 0 and frequency as an empty map. In the first iteration, we process the number 3. The complement is also 3, but since 3 is not yet in the frequency map, we add it, resulting in frequency equals 3, 1, and the count remains 0. Next, we process the number 1. The complement is 5, which is not in the frequency map, so we add 1 to the map, making frequency equals 3, 1, 1, 1. The count is still 0. Now, we process the third number, which is another 3. The complement is again 3, and this time, 3 is present in the frequency map with a frequency greater than 0. This allows us to form a valid pair, 3, 3, we decrement the frequency of 3 by 1, updating the map to frequency equals 3 o'clock, 1, 1, and increment the count to 1. In the fourth iteration, we examine the number 4. The complement needed to sum to k is 2, but since 2 is not in the frequency map, we add 4 to the map. The frequency map is now frequency equals 3 o'clock, 1, 1, 4, 1, and the count remains 1. In the fifth and final iteration, we process another 3. The complement is again 3, but since the frequency of 3 in the map is currently 0, we cannot form a pair. Instead, we add this 3 to the map, updating it to frequency equals 3, 1, 1, 1, 4, 1. The count stays at 1. After processing all numbers, the final count is 1, corresponding to one valid pair, 3, 3, the output for this example is 1. In the third example, nums is 2, 2, 2, 2, and k is 4. We begin with count set to 0 and frequency as an empty map. In the first iteration, we process the number 2. The complement is also 2, but since it is not yet in the frequency map, we add 2 to the map, making frequency equals 2, 1, and the count remains 0. In the second iteration, we process another 2. The complement is again 2, and this time, it is present in the frequency map with a frequency greater than 0. This means we can form a valid pair, 2, 2. We decrement the frequency of 2 by 1, updating the map to frequency equals 2 o'clock, and increment the count to 1. In the third iteration, we process yet another 2. The complement is still 2, but since the frequency of 2 on the map is currently 0, we cannot form a pair. Instead, we add this 2 to the map, updating it to frequency equals 2, 1, and the count stays at 1. In the fourth and final iteration, we process the last number, which is another 2. The complement needed is 2, and since it is present in the frequency map with a frequency greater than 0, we can form another valid pair, 2, 2. We decrement the frequency of 2 by 1, updating the map to frequency equals 2 o'clock, and increment the count to 2. After processing all numbers, the final count is 2, representing two valid pairs, 2, 2, and 2, 2. The output for this example is 2. To analyze the time complexity of the given solution, we start with the initialization of variables. Setting up count equals 0 and creating an empty dictionary frequency equals our constant time operations, or O1. Next, we have the main operation, iterating through the array nums using a for loop. This loop processes each of the n elements in the array exactly once, so it contributes O(n) to the overall time complexity. Within the loop, the code performs several dictionary operations. For each element, it calculates the complement as k number, checks if this complement exists in the dictionary, and updates the dictionary accordingly. These operations, complement computation, dictionary lookups, and updates, are all O(1) on average, thanks to the hash table structure of Python dictionaries. Since these operations are performed once per array element, they add up to O(n) across the entire array. Therefore, the total time complexity of the algorithm is O(n). Now, combining all the steps, we confirm that the overall time complexity is O(n). Moving on to the space complexity, the solution uses a dictionary, frequency, to store the frequency of numbers. In the worst-case scenario, if all the elements in the array are unique and none of them form valid k-sum pairs, the dictionary will need to store all n elements. This means the space required for the dictionary is O(n). Additionally, the algorithm uses a few single-value variables like count and complement, which require only constant space, or O(1). Since these variables do not scale with the size of the input, the total space complexity is dominated by the dictionary, making the overall space complexity O(n). Let's compare this optimized solution to a brute force approach. In a naive solution, we would check all possible pairs of elements in the array to find those that sum to k. This involves iterating through every pair, which results in O(n) superscript 2 time complexity, as there are approximately n*(n1/2 pairs to check. On the other hand, the brute force approach typically uses no additional data structures, so its space complexity is O(1). The optimized solution, however, significantly reduces the time complexity to O(n) by using a dictionary to track frequencies, enabling constant time lookups and updates for each element. While this improvement in time efficiency comes at the cost of using O(n) space for the dictionary, the trade-off is highly favorable for large input sizes. Let's take a closer look at the best, average, and worst-case scenarios for this solution. In the best case, if all elements in the array can immediately form valid k-sum pairs as we iterate through them, the dictionary remains relatively small. Even in this case, the time complexity is still O(n), because we must process every element in the array. In the average case, for most input distributions, the solution performs efficient dictionary operations while iterating through all elements, keeping the time complexity at O(n). In the worst case, no valid k-sum pairs exist, meaning the dictionary will store all n elements, resulting in O(n) space usage. However, the time complexity remains O(n), since dictionary operations like lookups and updates are O(1) on average. Finally, the mathematical justification for the big O notation reinforces this conclusion. The single for loop processes each of the n elements once, and each iteration involves constant time operations. Similarly, the space required is proportional to the number of unique elements in the array, which is at most n. This balance of efficient time performance and manageable space usage makes the solution well suited for large datasets. One of the most common mistakes in solving this problem is relying on a brute force approach. This involves iterating through all possible pairs in the array to check if they sum up to the target value, k. The issue with this method is its quadratic time complexity, O(n squared), which becomes impractical for large input sizes, such as when n approaches 100,000. This can result in time limit exceeded errors. A far more efficient approach would be to use either a hash map or a sorting in two-pointer technique. Another frequent mistake is modifying the array directly while iterating through it. This can cause unintended behavior, like skipping elements or encountering index errors. Instead, you should use strategies like adjusting the frequency map in the hash map approach or simply manipulating indices in the two-pointer method. Lastly, overlooking edge cases is a critical error. These include scenarios involving duplicate values, arrays where all elements are the same, or cases where there are no valid k-sum pairs. Failing to account for these can lead to counting errors or incorrect results. To avoid this, always test edge cases thoroughly, particularly when k is very small, very large, or when the input contains repeated elements. Another issue to watch out for is the incorrect use of a hash map. For example, forgetting to decrement the frequency of an element after it has been used in a pair can lead to overcounting or undercounting valid pairs. It's essential to update the hash map correctly after processing each pair to ensure accurate results. Additionally, some may overlook the benefits of sorting the array as a pre-processing step. While sorting adds a time complexity of O(n log n), it simplifies the implementation of the two-pointer approach, which is more efficient than brute force. Skipping this step can lead to unnecessarily complex or inefficient solutions, so consider sorting whenever the problem constraints allow. These adjustments can help ensure your solution is both correct and optimized. When tackling this problem in an interview setting, there are a few key insights to keep in mind. First, recognize that this is fundamentally an extension of the two-sum problem, which is a classic pattern for applying hash map or two-pointer techniques. Highlighting this connection can demonstrate your ability to identify and adapt familiar patterns. In terms of an optimal approach, hash maps are generally the preferred solution due to their linear time complexity, O(n). However, the sorted two-pointer approach is also valid and can showcase your flexibility. It's also important to clarify constraints with the interviewer. For instance, ask whether the array is mutable and confirm how to handle edge cases like negative numbers, duplicates, or empty arrays. Be sure to discuss trade-offs too, such as the extra O(n) space required by hash maps versus the O(n log n) sorting overhead of the two-pointer method. Finally, explaining how your solution addresses edge cases, like arrays with no valid pairs or arrays where all elements are identical, can demonstrate thoroughness and attention to detail. This problem is closely related to a number of other classic coding challenges. The most direct connection is with the two-sum problem, LeetCode number 1, which involves finding a pair of numbers that add up to a target value using a hash map. Extending this logic, there's the three-sum problem, LeetCode number 15, where you're working with triplets, typically solved using sorting in two pointers. Similarly, the four-sum problem, LeetCode number 18, builds on this idea to find quadruplets, often requiring nested loops alongside sorting. Another related challenge is the partition array into disjoint intervals problem, LeetCode number 915. While it's not directly about k-sum pairs, it involves array splitting and optimization techniques, making it a good exercise for improving your overall array manipulation skills. Exploring these related problems can deepen your understanding of patterns and techniques that are widely applicable in array-based challenges. There are several approaches to solving this problem, each with its own trade-offs. The hash map approach is highly efficient, with a time complexity of O(n). Here, you store the frequency of each number in the map, and for each number x, you check if kx exists in the map. While this method is fast, it does require additional space, with a space complexity of O(n). Another option is the sorting in two-pointer approach. By sorting the array first, you can use two pointers, one starting at the beginning and the other at the end, to find pairs that sum to k. This approach has a time complexity of O(n) log n, due to the sorting step, and a space complexity of O(1) if sorting is done in place. While slower than the hash map method, it uses less space, making it a good choice when space is constrained. Lastly, there's the brute force approach, which involves checking all possible pairs. While this method is simple to implement, its O(n)² time complexity makes it unsuitable for large inputs. Understanding these alternatives and their trade-offs allows you to choose the most appropriate approach based on the problem constraints and requirements. Great job! We've covered key techniques to solve the max number of k-sum pairs problem efficiently. Remember to practice using hash maps for similar problems, as they're a cornerstone of competitive programming. Thanks for joining, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!